positive potential energy. So it can convert the positive potential energy to kinetic energy, which is why above the data line, potential energy will always be positive. Okay. Therefore, sign is important. Otherwise, if you not put the negative sign here, you're going to ruin the whole thing. So we know that the first one is 0 plus this thing here, 15 times 9.81 times 0.15 times 1 minus cosine 30. Cosine 30 is 0.86 roughly, equals to 1/2 of 15 times 0.15. This is the I, remember? 1/2 of I times what? 1/2 of I times omega squared. So this is going to be omega 2 squared plus 0. This is 0 because it's a data line. And the whole thing has only one unknown, omega 2. So this omega 2 means that when the disk swings back to point B, right before it hits it, it carries this omega 2. So of course, we can find out the value of omega 2. Omega 2 can be found to be 3.418 radians per second. Now, when it regards the sign, you also want to be careful. If you want this to be positive, which means we already assume the positive direction. So what's the positive direction of this in this problem? If you want this to be positive, because we didn't say this is square, right? So omega 2 actually can be positive or negative. So now is your choice to define the positive direction. So please do not assume that omega 2 will always be positive, because we're going to take square. So even when omega 2 is negative, the whole equation is still true. So here, if you want to write this to be positive 3.418 radians per second, you have to define the positive direction. And we choose to write it this way because we want this to be positive. That means we already decide the positive direction. So what's the positive direction here? The positive direction here is clockwise or counterclockwise?
Counterclockwise?
Counterclockwise, right? So it goes this way. Why it goes this way? Because it swings like this. We assume this to be the positive direction. That's why we write this like this. If you don't like this definition, you like to write this omega 2 is negative. That's okay, because this will still be true, because we're going to take omega 2 squared. Now, step 2. Once we have this figured out and everything else is much easier, step 2, we'll just solve this problem, which is from what? From T2, which is this moment, to G double prime, which is the highest angle, theta maximum. So we're going to write this. We're going to say that T2 plus VG2 equals T3 plus VG3. Now look at this, because at T2, we set this position as the data line. So the potential energy, in any case, is going to be 0 anyway. That means the VG2 will always be 0. Right? Because that's what we said is a data line. So omega 2 here, this guy is always going to be 0. Now, because we want to find out the maximum angle, that means I don't care how high this center is going to move, but it must be at the moment when there's no angular velocity. Because if it has the angular velocity, it will keep moving up. So the maximum moment must be at the position when the kinetic energy is completely consumed. So here, T3 is going to be 0 when theta becomes maximum. Would you agree? Right? If it's not the maximum, it will just keep moving up. But when it moves to the maximum, there's no kinetic energy here. So all we have to do is to plot the whole thing back. And T2 is 1/2 times I. I is 1, IA. IA is 1/2 times 15 times 0.15. Of course, you can just use a numerical value, but I think we can just copy it this way. Times omega 2, that's 3.418 squared plus 0 equals to the potential energy. Remember, it's above the data line, so it's going to be positive. So this is going to be 0 for the kinetic energy at T3 plus, because it's positive, M15 G AG times 9.81 times what? Times the height, right? And we already know that this equals to 0.15 times 1 minus cosine. Now, before we know the angle was 30 degrees. Right now, we don't know the angle. So you're going to assume this to be theta maximum. So this is cosine theta maximum. Once again, we have one equation for one unknown. Can we find it? We can determine the value of theta maximum, right?
Yes.
Now, there's one little problem here. We actually make one mistake. So what's the mistake I make here? Which part went wrong?
Is it the height squared?
No, the height is okay. Height, right? M, G, H. This is correct. But what happens to impact? Right? What happens to impact here? So where's the mistake? The mistake
is
this value.
direction.
The angular velocity. We use exactly the same angular velocity. We assume that when it hits it, this is the angular velocity when it comes back. Turning from the wall.
Negative now.
True. And not only it should be negative, but the value of this, we use exactly the same value as the impact. So we assume that the incoming velocity, angular velocity is 3.418, and the outgoing angular velocity, we also assume this to be 3.418. That means we assume the E to be 1, which is not true. So this value cannot be the same angular velocity as before. It should be smaller because of this E, coefficient of restitution, is not unity. So the mistake we make mostly is here. This thing should not be 3.818. It should be something smaller because of impact. Would you agree? Right? So we actually solve the problem. If you write it this way, you assume that this interface E actually has a value of 1. That if you assume that, and this will be correct for that assumption, that you can find out the maximum angle. Of course, in this case, theta was going to be 30 degrees. And there's no fun in this example anyway, because we already know the initial angle is 30 degrees. Therefore, this cannot be 3.418. So what should this one be? This has to be determined by the coefficient of restitution. So we're going to say this. The coefficient of restitution is 0.6. That equals to VB2 minus VA2 divided by VA1 minus VB1. Now we're going to assume that the disk is A and the wall is B. All right. So if we assume that, and if you assume that, you know that because the wall will never move, so the VB2 is going to be 0. VB1 is also going to be 0. They don't move, right? Well, the wall doesn't move. That makes sense? Then all you have to do is here, just to calculate that. So here we have 0 minus, now this regards our assumption. What is the initial velocity we will assume? And of course, what we plug in here is linear velocity, right? But because for this object, it has a constant radius, so you could actually use the angular velocity here, and they will cancel out. Because in order to find out the linear velocity at this point, you're going to multiply this angular velocity with the radius. And the radius is constant, so every one of them is subjected. Every one of them in this expression of restitution, coefficient of restitution, is subjected to constant radius. So you can cancel it out. Therefore, we can just write the omega 2 here. So the actual omega 2 you can plug in here is not 3.418, but it should be determined from here. Now the initial omega 2 here is what? Is BA1 is the initial one. So that down here is a 3.418. Remember, we assume this to be positive direction, right? So this is going to be plus this minus omega 2. So this is the true omega 2 you can use. Now, because it's subjected to a negative sign, so you're going to find out omega 2 to actually to be what? To be negative 0.6 times 3.418, which is a negative 2.0508 radians per second. Now, this result has physical meaning. First of all, the magnitude is less than 3.418. So that is the true value which you plug in here. You should plug in negative 2.0508. Put in to replace with 3.418. And this is negative. Why? Because after the rebound, it changes its direction. And we already assume that the positive direction is counterclockwise, right? That means under the assumption or under the assumed counterclockwise positive direction, the answer is negative, which means that it goes in clockwise direction. So the rebound angular velocity goes like this. That makes sense, of course, because of rebound. So after replacing 3.418 with the negative 2.0508 into this expression, we have one unknown, which is the angle, and with one condition, so we can determine the value of theta maximum. Correct? Then we can really find out the value of this. And this value is much less than, of course, 30 degrees. So from here, theta maximum is 17.9 degrees. Okay? Is that clear?